In industrial biotechnology, a paramount objective is to go from research to commercialization. This requires scale-up of the process from lab to the factory. Now, why is that? Why are industrial processes big? Well, investment costs scale with equipment area. Basically, you buy equipment walls, steel or concrete. Also, operation costs often scale with heat losses, which is related to the area. Further, instrumentation costs scale with the number of reactors, not their size. Capacity, however, scales with volume. So we see that upon scale up, the total costs go down with capacity to the power 2/3. In general, depending on the specific equipment, this factor is between 0.5 and 1. Scale up comes with risks. Very often there are scale effects and the performance of a process changes with scale, where usually it is lower on the large scale. Dealing with these risks has resulted in two main approaches applied in the industry, either innovative or conservative. While the innovative one is increasing in size to capture the economy of scale with examples as stir tanks, power plants, airplanes and bridges, the conservative other is increasing in numbers. This means copying large numbers of smaller equipment to achieve the required volume, and this approach is of course less risky. Examples are membrane reactors, compressors, solar panels and computer clusters. But also fermentation plants usually have about 4 to 6 bioreactors in parallel. In the factories, processes are performed at scales of tens to hundreds of cubic meters. In special cases, even thousands of cubic meters. And this means linear dimensions of tens of meters and volume-specific wall areas or area per volume more than 100 times less than at small scale. This is the basis of significant scale-up issues. And moreover, there is usually limited time and budget to solve issues. The toolbox of an industrial process engineer therefore contains different instruments, depending on the urgency and magnitude of the issue to solve, using less or more mechanistic information, applying simple or fundamental mathematics, and accepting no or sizable risks. When errors and mistakes are ruled out, scale-up issues in biotech processes are usually related to poor mass transfer or poor mixing, while poor heat transfer is occurring less often and can be prevented using good engineering design practice, applying enough cooling area and low cooling water temperatures. Cells thus are facing non-ideal conditions, such as steep glucose concentration gradients, moderate oxygen transfer rate gradients resulting in local oxygen depletion, and usually mild CO2 concentration gradients. Further, cells may undergo cold shocks of 5 degrees centigrade every 10 or 20 minutes. It is clear we need robust organisms. It is also important to realize that not all cells are equal. They face different environments and adapt accordingly. This can be best illustrated by so-called lifelines of individual cells. The figure shows how they may vary for 3 different cells. For scale-up, we always advocate the philosophy begin with the end in mind. This means that before scaling up, you should scale down first. Scale up starts at the commercial scale. All research in the lab should be done under representative conditions, mimicking the cellular environment from the industrial scale in the lab as much as possible. If the industrial bioreactor is already up and running, key information can be retrieved on the rate-limiting compound, the CO2 concentration, the average time and amplitude of fluctuations in the limiting substrate concentration, the oxygen concentration, and frequency and magnitude of cold shocks. With this information, the scale-down simulator in the lab can be designed and operated. However, when no information from industrial scale is present, then we still advocate that it is always possible to make a reasonable estimate, using basic insight in scale, geometry and transport phenomena, and possibly some key assumptions on properties of the cells. In recent years, high-resolution computation methods have proven useful to calculate or estimate what cannot be measured, and this trend certainly will gain traction in the years to come, allowing detailed insight in the large-scale process with high fidelity, even without limited measurement data available. Various scale-down simulators have been proposed and tested in the labs. Roughly, there are two categories. 2 or 3 interconnected compartments with broth recirculation and feeding or aeration in only one of the compartments. The units can be stir tanks or plug flow reactors, often with some axial dispersion. On the positive side, this probes the performance of the culture in which cells get different exposures to the conditions. Fast changes, slow changes, and also with smaller and bigger amplitudes. However, a downside is that one needs pumps and recycle loops, which is complex to execute and could bring artifacts, such as shear damage by the action of the pump or nutrient depletion in the loop. A single reactor in which the conditions are varied by on-off feed and/or aeration and oscillating stir speed is the other option. In this way, variations in space are translated to variations in time. This is simpler to execute, however, cells are always in the same environment, which is not the case in reality. This could be overcome by deploying a variable operation protocol with fast and slow sugar pulses or other feedstock pulses and continuously changing aeration conditions. I advocate that when you manage to apply the scale-down method in this way, that scale-up surprises can be minimized. And I would like to quote here a somewhat provoking statement from one of my former industrial teachers, who once said, "If there is a difference in performance when comparing lab scale and industrial scale fermentations, then the problem is in the lab." Now, this may not always be true in reality, but it is an interesting food for thought. With this, we have arrived at the end of this week. In the next week, we will move from the upstream section of bioprocesses to the downstream operations, in which the components present in the fermentation broth need to be separated and purified. Thanks for joining, and see you there.